Okay. Hi, everyone. Thank you for coming. My name is Dana Jacobsen, and I'm going to be talking about random numbers in Perl. I've written a number of CPAN modules, or a few, given that some of the people here have written many CPAN modules, for random number generation and cryptography. But I spent a lot of time on my ntheory module for number theory, which does things like random primes, random integers. Some factoring algorithms actually want random numbers. And in the past, I'd been using bytes random secure, which is in pure Perl, and it uses Isaac under the scenes. But for various reasons, I wanted to move to C, and I wanted to look around and see what was out there. I ended up moving to Cha-Cha 20, and I wrote a blog article about this in April, and looked at a whole bunch of different modules. So this isn't really going to talk about my module, Cha-Cha 20, so much as what I found when I was looking at all the other modules doing RAND. So one of the things I'm going to talk about is what do we want from RAND, or at least what I think we want from it. A little bit about pseudo-random number generators and some of the CPAN modules that are out there. Some things I'm not going to talk about. Entropy, I gave a talk last year about user space entropy, why you should not do it, and why it's a whole lot of fun to do it anyway. I'm not going to talk about cryptography in any detail. There are other distributions, not going to talk about that. And I'm not going to talk about seeding and reseeding details. All very interesting topics. If I had a longer talk, I'd probably talk about them. So here's some of the modules I found. This blog article talks about a lot of these. And most of these, you've got core RAND, but you also have a number of modules where you can just plug and play. You put in your line to use them, and suddenly RAND and SRAND are replaced with the version from that module. What do we want from RAND? So these were the 7 things I thought we wanted from RAND. And I'm going to talk about these, each one. So we want consistent semantics. So an example of not consistent semantics is the way a lot of these modules do integer random number generation, because there's no standard out there, so everyone's kind of just found their way. We may or may not have an IRAND 32 and 64 to get 32-bit and 64-bit values. There may or may not be an IRAND function, and if there is, it might give 32, it might give 64. In the case of one module, it depends on your platform. It'll just choose one for you. However, for floating point random numbers, we do have fairly good standards. Well, it's in the Perl core, so everyone's trying to follow that standard. You have SRAND, where you can actually seed the random number generator, and then RAND returns the half open interval 0 to 1. That is, it'll return 0, it'll return some floating point number up to, but not including 1. And we can give it another value, like an n, as an argument, and it'll go up to that. And so there's a good reason we use the half open interval, because generally you do something like, I want a 6-sided die, so I add 1 to the result of RAND 6. Well, if it returned 1, I could roll a 7 on a 6-sided die. That's generally not what you want to do. So there are a couple modules out there that get that wrong. It's fairly subtle. You'll hardly ever see it, I should say. The problem is every now and then you do. So we'd like it to do that correctly. We'd like performance. All other things being equal, we might as well have it fast. If I'm doing a simulation, I don't want to spend my time getting random numbers. I want to spend my time doing my simulation. I don't want it slow just because I'm getting random numbers. And the speeds vary. It depends what you think is fast. 29 million random floats per second from core RAND. We go down to 500,000 for some of the slower modules. For some people, that may be perfectly adequate. If you're doing database access in between, then this is all probably irrelevant. But if you're doing a simulation in a tight loop, that can be relevant. Note that the raw performance on the C code is much faster, or at least it's significantly faster than what do we get when we go through Perl. So, for instance, we'd say, oh, this cryptographically secure random number generator is really slow. And you see a lot of papers about this from people. But as soon as we start going through Perl, it really isn't relevant. It's really how tight can you make that interface from Perl to the C code. We would like well-filled output. So this one is a bit hard to describe in a short amount of words. So we want, from our rand function, we get an NV back. NV is the floating point representation that you've compiled in for Perl. And that could be a float, in which case we have 24 bits of mantissa we could fill. It could be a double, where we have 53 if you're clever. It could be a long double, which may be exactly the same as double, or it might be an 80-bit long double. Now you have 64 bits of mantissa. And if you use quad math, it gives you a true 128-bit floating point value. So now all of your floating point calculations in Perl are actually with 128-bit floats. So we have 113 bits to fill. So how many actually get filled? Some of them do 32. So wow, I compiled my Perl with 128-bit floats. I have all this stuff, and then you're filling in 32 bits. So now I have to start going through hoops to call it multiple times and fill it in. Core rand uses drand 48. The 48 is because 48 bits are filled in. Some of the others do more. Because I was deciding to make this on my own, I actually looked to see, oh, if you're in quad math, then I am going to fill all those bits. So I have to do multiple calls to fill it in. But I'll do that internally. So another thing we want is good seeding method. So when we have rand, we would like it to start at a different sequence every time, unless we manually tell it otherwise. So we'd like to use something like dev-urandom or the Windows crypto API. We know from many decades ago, using time is a bad example, a bad idea. It's very predictable. And we want to use a reasonable amount. That is, if we have a 32-bit internal state, it's really small, but if we had 32 bits, we don't want to read 10K from dev-urandom, trying to fill that in. On the other hand, if we have a large state, we also don't want to read too little, because now we're not getting the full value out of it. Some of the modules basically do everything. They will look for dev-urandom, they will look for the crypto API, and they will have fallbacks. These two do everything except the window. They don't look at the Windows API. Core rand and mathrandom mtwist do a good job. They will look at dev-urandom, they will look at some system things for backup, but they only fill in 32 bits. So it really isn't as much as those could really use. And then, like mathrandom Isaac just punts on the whole problem and says, I'm not going to seed, you figure that out. Which may be perfectly appropriate for you, but it may not. It does mean that now you have another problem to figure out. Mathrandom Xorshift uses time, and then mathrandom MT just uses rand to get its seed, which may be good, maybe not. Repeatability is something we want. We want some manual seeding method, and we want it for simulations, for instance. So you run your simulation, you know the seed value you started with, you're getting statistically random numbers as you go along, but your simulation does something strange. And you say, well, I'd like to repeat that. So this gives you the ability to do that. Testing is another reason you often want repeatability. But crypto doesn't need this, and arguably crypto doesn't want this. And so crypt-prng, for instance, does not give you this, because that's not the point of that module. All of the other modules give you this ability. That's why there are pseudo-random number generators. They're not true random. So unpredictability is another thing we would like. So if I've seen one of your values, can I predict what you're going to have next? For crypto, absolutely, we do not want this. We do not want someone seeing one value and then going, oh, well, now I know what you're going to do for the rest of the time your program runs. For simulations, almost all of them, we assume we're not having an adversary there watching the output. So for many purposes, it's irrelevant. It doesn't mean it's bad. It just means it's irrelevant. For drand 48, which is used in core rand or Xorshift, takes one value. If you've seen one random number, you know them all from all the sequences. If you actually didn't know the parameters for drand 48, but you knew what type of algorithm it is, you need two values. For the Mersenne Twister, it's giving away its state every time. As you call, 624 values, and you know every value that will ever come out of that Mersenne Twister. For PCG and however you want to pronounce that, Xorshift 128, it's an XOR, so maybe it should be Xorshift. There's no really known method to get that, but on the other hand, the authors point out there's no particular reason you could not find a method to do it. And then the cryptography methods, so Isaac, Salsa 20, Cha-Cha 20, and so on, that's kind of the point of them, is that if you could find a way to predict future values from past values, well, you've broken the code. And no one has broken those yet. So they are arguably as secure as hash functions. So statistical quality. This is the thing most people talk about. Knuth spends 170 pages talking about random number generators and how you measure them, how you could find things that are wrong with them. He also tries to write his own and then points out it's a lot harder than I thought it was. There are programs such as DieHard, DieHarder, TestU01. Each of those comes with multi-100-page manuals describing all of the tests they perform, what they mean, how you get those results. So let's look at system RAND, used before 5.19.4. System RAND is like a box of chocolates. You never know what you're going to get, but it's probably bad for you. So this is an example from the 1960s. This is a particularly egregious example. Looks kind of random. This is an XY plot where we take one value, mark it on the X. We take the second value, mark it on the Y. You want to see something that's kind of random. This is not a statistical test, but it's a good kind of first approximation. You look at it, it looks kind of good. And then we use seed 128. Well, that doesn't look right. 2 to the 16th, that really doesn't look right. What if we started with this seed value? There's one dot in the center. Not a good random number generator to use. So DRAND 48, made in the late 1980s, fairly standard, and Perl 5.20 uses it everywhere. The great advantage there is it is uniform. So no matter what platform you're on, Windows used to have one with 16-bit period, so you'd get the same cycle repeating over and over. So DRAND 48 is a little nicer than that, and that looks good. And we'll start looking at some numbers. Here we're just going to look at the full 48 bits, because it's a 48-bit result. And we might notice, if you look at enough of them, that all of the last digits, we go odd, even, odd, even, odd, even. And if you look at the binary pattern, you get 1, 0, 1, 0, 1, 0. And worse, you start looking at the next bit over, it goes 0, 0, 1, 1, 0, 0, 1, 1. And then we go 0, 0, 0, 0, 1, 1, 1, 1, etc. This particular one doesn't show really obvious patterns after that, but they do exist. So this is the result where I took the lower 24 bits and chose every 256th value. And we start seeing these patterns. So this is not good. And indeed, if you run TestU01, the small test, it fails 5 of those tests. But it's better than a lot of random stuff you might get, pun not intended actually, when you use system RAND. So Mersenne Twister from 1997 was a big deal and probably still is. It uses a huge state, which is either good or bad. It's reasonably fast. There are SIMD versions that are quite fast. Has an enormous period, meaning when are you going to see the same thing cycle over again? You're not. And it passes all the TestU01 small tests. However, it does fail a few of the more comprehensive tests that we've come up with lately. It is used in a few places. Perl 6 uses it, Python uses it, Julia, Maple, MATLAB. It's used in the GMP library. And we have a few modules that use it. MathRandom MT, and then MT Auto, what that did is make it a little faster and then give you seeding. And then mTwist is a faster yet version. So Xorshift, Marsaglia has been, God, I think he's been doing this for 50 years. So he came up with this idea in 2003 of let's make something really simple that can still pass a lot of these tests. Well, it doesn't entirely pass all the tests, and MathRandom Xorshift actually implements this. So he then said, well, okay, well, we can fix that up a little bit. We'll make Xorshift star, and then Xorshift 1024 star, and Xorshift plus, and so on. So the good thing is the last one passes all the tests. Still fairly simple. Here's some C code that I don't really expect you to read, but it's fairly simple. It just does XORs, shifts, rotates. And it passes all the comprehensive tests. Melissa O'Neill wrote a very large paper about random number generators, history of random number generators, and the PCG family, and did a 1-hour video, which you can find on YouTube, talking about this if you really, really care about random number generators. And it's also shifts, XORs, and rotates. And it's very fast. A lot of these are the kind of the modern ones, passes all the tests, and arguably this is the best of the new generation. So new meaning in certainly the last 10 years. And cryptographic random number generators, there's Isaac. Isaac gets used a lot in Perl because there's a module out there and it was written a long time ago. And it works quite well. Large state, hasn't been broken, gives you wonderful graphs, passes all those tests. Cha-Cha 20 is where a lot of people are going. Fairly small state, but certainly large enough. It's very fast and allows for very, very fast SIMD instructions if you want to write your code in assembly. So Linux moved to Cha-Cha 20 in dev-urandom, and arc4random in some of the BSDs has moved to Cha-Cha 20. And we now have both XS and pure Perl module. I wrote that. And then CryptPRNG was using Fortuna, which is a whole framework. They switched to Cha-Cha 20 because it's faster and it's a little more standardized. So the last thing I want to talk about is this idea of a configurable rand for the Perl 5 core. By that I mean compile time. So we actually do this for hash functions. If you look in the Perl 5 source, you can see we actually implement a whole bunch of hash functions, and you pick whatever you're going to use. Most people will probably never change those, but they're out there. They're has the ability for anyone who's interested in testing different hash functions to try it out. And if one's better, we can go to it. So it'd be interesting to try this. I have a start at it for both Mersenne Twister and the other two modern ones. The big bottleneck is it must be portable even on really crazy systems, and endianness, 32-bit, a lot of interesting things. When you get into the Perl 5 core, you definitely want it to be portable. And my final thoughts. So the DRAND 48 moving to something else, because we've seen that worked really well in the late 1980s, but we've learned a lot since then. So it'd be nice to move to a more standard random number generator. If you just want fast, simple random number generator, MathRandom mTwist is a really good choice. It's very fast, works well, uses Mersenne Twister. And ntheory is my module, and it uses a fast Cha-Cha 20. And that's it. That's where I plan to be.